Chapter 3, Module 3. We all know that category theory is by itself a branch of study in mathematics. Since the language of categories and functors sometimes help to understand certain complicated situations very nicely, we shall introduce in this module in a very informal way what we mean by categories and functors. We shall also observe several examples of categories and functors. A category C consists of 3 items: a class of objects which will be denoted by the letters A, B, C, etc. For each pair of objects A and B in C, a set Hom AB, which is called the set of morphisms or arrows, and we denote the members of the set Hom AB by F, G, etc. A product Hom AB cross Hom BC to Hom AC for each triplet ABC of objects in C, called composition, denoted by G composed F belonging to Hom AC for the members F from Hom AB and G from Hom BC, such that the following 2 conditions are satisfied. First one is associativity, that means for any morphism F in Hom AB and any morphism G in Hom BC and a morphism H from Hom CD, we must have H composed G composed F is equal to H composed G composed F. Secondly, existence of identity, which says that for each object A in C, the category, there exists a morphism I, a specific one, which satisfy the following conditions: that when F is taken from Hom AB and G is taken from Hom CA, then F composed IA is equal to F and IA composed G should be equal to G. Among various examples, we only cite the examples of categories that we are interested in this course. The first one is the category of sets and mappings. We denote this category by set, where the objects are taken as sets. The arrows or morphisms are basically the mappings, and the composition is the usual composition of mappings. In the second example, we take a category GRP, which has the objects as groups. Arrows or morphisms between 2 groups G and H are the group homomorphisms, and the composition is the usual composition of mappings. The category AB consists of the objects as the abelian groups, the arrows as the usual group homomorphisms, and the composition as usual as the composition of mappings. Another example is from the topological spaces. We denote the category by top, where the objects are topological spaces, and the arrows between two topological spaces x and y are the continuous maps f from x to y, and of course, the composition is the composition of maps. This category is also very important, the category of pointed topological spaces and the continuous base point preserving maps. We denote this category by top star, where the objects are pointed spaces like capital X, and a specific point x is taken from capital X. So, the objects are the pairs capital X comma small x, as well as capital Y comma small y, where we take the point y, the small y, from the space capital Y, and so on. Here the arrows are the continuous functions from xx to yy, such that it preserves the point x to y. The objects in the example cited above are all of the type set with an additional structure, and the morphisms are certain functions, but that is not the case in general. To distinguish this class from the most general ones, these categories are sometimes referred to as concrete categories. So far as our course is concerned, we are interested in concrete categories only. Now, we try to visualize what we mean by a functor. Intuitively, a functor carries the structure of a category to another. That means, a functor needs to preserve objects of the categories as well as the morphisms. Now, let us try to formalize this intuitive understanding. We take two categories, one is C and the other one is D. A covariant functor from C to D, which we denote by F from C to D, consists of two things. First one, an object function which assigns to every object A of C an object F A of D, and we denote it by A maps to F A. Secondly, an arrow function which assigns to every morphism F of Hom A B of the category C a morphism F F which belongs to the Hom set F A F B of the category D, denoted by F maps to F F, such that two conditions are satisfied. The first one is F of 1A is 1 of F A for each object A of C. Here 1A stands for the identity morphism from A to A in the category C, and 1 F A stands for the identity morphism from FA to FA in the category D. So, in the first condition actually we are asking for the identity morphism of C to be carried by the rule F to the corresponding identity morphism of D. Second condition is that if G composed F is equal to Fg composed Ff for any composable pair of morphisms in C. That means, whenever we have a commutative diagram in the category C of morphisms, it will be carried to a commutative diagram of morphisms in D by the rule capital F. Let us take an example of a functor. It is a very natural one. If we consider the category set, here the objects are sets and the morphisms are simply mappings. Define a functor P from category set to the category set itself by PA is equal to the power set of A for each object A of C. For any F taken from Hom AB, PF will be in Hom PAPB, which is given by PF on S is equal to Fs whenever S is a subset of A and Fs is in B. We observe that P of 1A is equal to 1 of PA and P of G composed F is equal to PG composed PF. So, P is a functor from the category set to the category set, and this particular functor is called a power set functor. This example is a very typical one. The name of the functor is forgetful functor. That means, it forgets the structure of the domain category. That means, if we take a functor F, we want to define a functor F on the category GRP of groups and group homomorphisms to the category set of sets and mappings, it takes the group to the underlying set of the group. That means, F will take the object G, which is a group in the group category, to the underlying set of the group in the category of sets. And when F is operated on a morphism F, then that will be carrying the morphism, which was a group homomorphism, to the underlying mapping F. So, that means, when we are starting with a morphism, a homomorphism from a group to group, then that homomorphism is actually a function which preserves the group structure. So, the functor forgets the extra condition of preserving the group structure and gives us back the same F as a mapping inside the category set. Similar thing happens when we take the category top and want to define a functor from top to set. by applying the same technique. That means, we start with a topological space x tau, the functor will take that topological space to the underlying set X, which lies inside the category set. Any morphism f from x tau to y sigma in the category top is basically a continuous function from x to y. So, f will be the same f, but it will be the mapping from x to y, ignoring its continuity, as there is no topology on the sets x and y in the category set. This way, we can define several more forgetful functors, like a forgetful functor from ring to set. It may be a forgetful functor from ring to abelian groups, and so on. Now, we talk about a specific type of elements, rather objects, in the concrete categories. Suppose capital F is an object in a concrete category C, X is a non-empty set, and I from X to F a morphism in the category set. F is called a free object on the set capital X if for any object A of C and a morphism F from X to A, there exists a unique morphism of C G from F to A such that G composed I is equal to F. This composition is taking place inside the category set. Now, two objects A and B in a category C are equivalent if G composed F is identity and F composed G is identity. With these informations, we state a theorem which says that if C is a concrete category, F and G are objects of C such that F is free on the set capital X and G is free on the set capital Y, and also the cardinality of the set X is equal to the cardinality of the set Y, then we can conclude that F and G are equivalent as objects. Clearly, the category of groups and group homomorphisms is an example of concrete category. So, the question is, can we get examples of free objects in this category? We shall see next that yes, of course, we do. There are examples of free objects in the category of groups and group homomorphisms. Not only that, we shall learn how to construct free objects in this particular category of groups and group homomorphisms. The infinite cyclic group Z of integers is a free object in the concrete category GRP of groups and group homomorphisms. Why so? Let us take any group G and take any point x from G. The homomorphism G from Z to capital G given by Gn equal to x to the power n is the unique homomorphism such that it maps the integer 1 to that particular element x of capital G. So, choosing capital A as the group G, capital X as the singleton set 1, I from x to z as the inclusion map, and f from x to G given by f of 1 equal to x in the definition of free objects, we get that Z is free on the set singleton 1. This example shows that free objects exist in the category GRP. With this, we define free group as a free object in the concrete category GRP. Given a set capital X, we shall now see the construction of a group F that is free on capital X. Case 1, if we take capital X as empty set, then the trivial group consisting of only the identity element serves our purpose. So, in the second case, we assume that capital X is non-empty. Then we follow the steps as described below to construct a group depending on the set capital X. We choose a set X inverse, that is just a notation. We denote a set by X inverse, which is a set disjoint from the given set capital X, and the cardinality of the set X inverse is equal to the cardinality of the set X. Since they have the same cardinality, there exists a bijection F from X to X inverse, and we write the image of any point small x belonging to capital X by Fx, and we denote that point Fx by the notation X inverse. Choose another set capital A, which is just a singleton, such that A intersection X union X inverse is empty. Denote the singleton set A by singleton 1. That means the single element of A by the notation 1. A word on capital X is a sequence A1, A2, etc., with AI taken from X union X inverse union 1, such that AK is equal to 1 for all k greater than equal to n for some n belonging to n. The constant sequence 1, 1, etc. will be denoted by 1, and it is called the empty word. A word is said to be a reduced word if the following hold: that for all x belonging to capital X, x and x inverse are not adjacent. That is, if AI is equal to x, then that will imply that AI plus 1 is not equal to x inverse, and if AI is equal to x inverse, then that will imply that AI plus 1 is not equal to x for all I belonging to n. And AK is 1 will imply that AI is 1 for all I greater than equal to k. So, in particular, empty word is always a reduced word, and any non-empty reduced word is of the form x1 to the power alpha, x2 to the power alpha 2, etc. up to xn to the power alpha n, and that is followed by 1, 1, etc. Here the point x is identified with x to the power 1, and we denote this sequence as x1 to the power alpha 1, x2 to the power alpha 2, etc. up to xn to the power alpha n. We observe that two reduced words are same if and only if one of the following holds. Either both are empty words, or m equal to n, xi equal to yi, and alpha I equal to beta I for all I equal to 1 to n. If fx is the set of all reduced words on capital X, then the map x to fx described by x goes to x to the power 1, which is x as we know, is an injective map. We identify capital X with the copy of capital X under this particular map and consider capital X as a subset of fx. We define a binary operation of fx following the scheme as follows, that we take two words. So, the operation is juxtaposition followed by cancellation of the terms of the form x to the power minus 1 and x to the power minus 1 x. This cancellation is termed as reduction. It is not hard to check that fx with respect to this binary operation of juxtaposition and reduction forms a group. Here the identity element is the empty word 1, inverse of x is x inverse, and it can be shown that fx is a free object on the set capital X in the concrete category GRP. In view of this theorem, we call fx a free group on capital X, and X is called the set of generators of fx. One can also establish that a subgroup of a free group is always free. In a similar way, a free object on a set X in the category AB of abelian groups and homomorphisms is called a free abelian group. It can be shown that an abelian group G is a free abelian group if and only if G is isomorphic to an internal direct sum of copies of the additive group Z of integers. In particular, the trivial group is a free abelian group on empty set, and we define something called a basis of an abelian group G as a subset S of G such that the following conditions hold: that G is generated by S for distinct x1, x2, xk from S and ni from Z, summation I equal to 1 to k, ni xi is equal to 0 implies that n1 equal to n2 equal to etc. equal to nk equal to 0. It can be shown that any two bases of a free abelian group F have the same cardinality. In view of the last result, we may define the rank of an abelian group, rather rank of a free abelian group F as follows. If X is a basis of a free abelian group F, then cardinality of X is called the rank of capital F. Finally, the following result establishes a connection between a free group and a free abelian group. It says that a free abelian group is a free group if and only if it is cyclic. There are a lot more to talk about free groups and free abelian groups, but so far as our course is concerned, it is enough to have this much of knowledge. With this, we end chapter 3.